Welcome to the clinic. Today, we are opening up the doors to a very special, highly targeted session that we are calling the Diagnostic Clinic. Look, if you have been grinding away, studying for the Cambridge AS and A-level computer science exams, specifically Paper 2, syllabus code 9618, you absolutely know the pain I'm talking about. It sometimes feels like you are literally memorizing a mountain of data, right? You're cramming in all these facts, you feel confident, but then you get your past paper back and you are still inexplicably losing marks. It's frustrating. It's incredibly frustrating. But today, we are stepping in as your lead physicians. We're going to diagnose exactly why those exam answers are failing. What are the symptoms of a weak response? And more importantly, we are going to prescribe the exact cure. We aren't just guessing here. We are using real data pulled directly from the Cambridge Principal Examiner reports. We're going to take their high-level insights and translate them into a concrete, step-by-step roadmap for your success. So grab your imaginary stethoscope and let's get to work. 15. I want you to just look at that number for a second. Why is this specific number so absolutely critical for you? Because the specific topic of instruction groups, specifically arithmetic operations, accounts for a massive 15% of your total marks in Paper 2. 15%. That is not a minor footnote. That is literally the difference between an average grade and a truly outstanding one. It's the difference between missing your university offer and securing it. It is a substantial chunk of the entire assessment. And yet, and this is the crazy part, it's an area where examiners see students repeatedly, year after year, dropping what should be easy points. They're making the same avoidable mistakes, while we are going to make absolutely sure you aren't one of them. Now, this right here is straight from the examiner's reports. Quote, top-performing students exhibit connected, conceptual understanding transferable to unfamiliar contexts. Let's break that down because this is basically the golden rule of the entire Cambridge syllabus. The examiners aren't looking for human hard drives. They really don't care if you can just flawlessly spit out dictionary definitions you memorized the night before. They are looking for agile thinkers. They want to see that connected, conceptual understanding. What does that mean? It means they want to see that you can take a core concept you learned in a very standard classroom setting and then seamlessly apply it to some completely bizarre, unfamiliar scenario they've thrown at you in the exam. You have to prove you actually get how the machine works, not just what the parts are called. To get you to that elite, top-performing level, here's our roadmap for today's clinic. First, we'll cover the 15% challenge. Second, the core operational principles. Third, the procedural framework. Fourth, we'll look at the top examiner warnings. And finally, we'll wrap up with critical analysis skills. Section 1, the 15% challenge. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. So when we talk about arithmetic operations in computer science, we're really talking about the underlying architecture of how a computer processes logic and numbers at the absolute deepest levels, right? It's the bare metal. To test if you actually grasp this, the examiners are specifically targeting 3 distinct cognitive domains. First up, knowledge and understanding. Basically, do you actually know the facts? Do you know what an arithmetic shift is? Second, application of concepts. Can you take those facts and use them in a specific scenario? And third, critical analysis. Can you evaluate the outcome of that application? Now listen closely, because this triad right here is exactly why simply memorizing a textbook is a recipe for failure. If your entire revision strategy only covers that first bullet point, just knowing the definitions, you are leaving the vast majority of your marks on the table. You might feel like you nailed the exam, but you'll get a C. Why? Because you didn't prove the application and the analysis. You have to demonstrate all 3 domains to get the top marks. Moving on to Section 2, Core Operational Principles. Master precise definitions, causal relationships, and cross-topic connections. I want to highlight something incredibly important from the principal examiner reports here. They explicitly note that candidates who reference cross-topic connections achieved significantly higher marks. But what does that actually look like in practice? Well, think of it like a giant puzzle. If an exam question asks you about a specific arithmetic instruction, and you can casually but accurately link it to how that instruction impacts memory addresses, or how it affects data structures that you learned about in a totally different chapter of the syllabus, boom, you are signaling to the examiner that you have that connected conceptual understanding we talked about earlier. You are showing them the big picture. You're basically saying, I don't just know this one fact. I know how this fact affects the entire computer system. That is exactly how you impress an examiner. All right. Section 3, the procedural framework. Think of this slide as the step-by-step anatomy of a flawless, top-tier exam response. One of the most absolutely critical foundational skills you need is data interpretation. For instance, you might have to take raw binary representations and extract the actual meaning from them before you even think about beginning your calculations. So here's your 5-step algorithmic thinking process. Step 1, deconstruct the question. Don't just casually read it. I want you to tear it apart. Find the command words. Is it asking you to evaluate, describe, or calculate? Step 2, extract relevant data. Pull out only the variables and binary figures you actually need. Ignore the fluff. Step 3, select your analytical framework. What kind of algorithmic structure does this specific problem require? Step 4, execute with clear notation. Write your code implementation or your math so cleanly that anyone on the street could read it. Don't make the examiner guess what your handwriting means. And finally, Step 5, present with correct terminology. Algorithmic thinking requires rigorous step-by-step decomposition, and strictly following this 5-step list is exactly how you mathematically prove your methodology to the examiner. And this brings us to a massive concept, the method mark strategy. This is an assessment approach where marks are awarded for your problem-solving process, not just your final answer. Listen, if you rush to the end calculation, make a tiny, silly arithmetic error, but you show absolutely zero working out, you get 0 marks, period. But if you follow those 5 steps we just looked at, write out your super clear notation, show your entire logical flow, and then accidentally make a small calculation error at the very end, the examiner can still award you almost all of the marks for your process. The journey is quite literally more important than the destination here. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, back to the clinic. Section 4, Top Examiner Warnings. Let's put our diagnostic hats on and look at the actual ailments that are constantly costing students easy marks. The principal examiner reports explicitly warn us about these top 3 recurring mistakes. First up, forgetting to check overflow and edge cases in arithmetic operations. Second, ignoring boundary conditions entirely. And third, providing generic answers that aren't tied to the context. I want you to use a visual story method in your head right now to encode this so you never forget it. Imagine a bucket. This bucket is overflowing with water because no one bothered to check the physical boundaries of the bucket. And to make it worse, the bucket is totally blank and generic. It has no label on it whatsoever. That visual represents the absolute easiest way to fail this section. When you write an algorithm, you must test it against the extremes. What happens if the binary number is simply too large for the register? What happens at the exact boundary of the data structure? If you don't explicitly mention these edge cases in your answer, you are bleeding marks. Now, what's really interesting about this slide is the contrast. This is a massive examiner alert. On the left, we have generic definitions. Let's call the student who does this Alex. Alex is the student who panics in the exam hall, sees a keyword, and just writes down the textbook dictionary definition of an operation, like an arithmetic shift, which simply shifts binary digits to multiply or divide. Alex writes that down perfectly, but completely ignores the scenario given in the prompt. Alex loses marks. On the right, we have context-applied reasoning. Let's call this student Sam. Sam links every single point to the unique scenario in the paper, whether the question is about a factory robot arm or a decentralized bank ledger. Sam explains how that arithmetic shift specifically impacts the robot's sensor data in that exact moment. Context is the ultimate key here. You must always link your knowledge back to the specific problem sitting right there on the page. Section 5, Critical Analysis Skills. All right, so we've diagnosed the symptoms, we've seen where students go wrong, now let's prescribe the ultimate cure. This right here is how you elevate your exam paper from a standard passing grade to an absolute standout excellent performance. Top-scoring candidates don't just write an algorithm, drop their pen, and walk away. They evaluate it. When you are asked to analyze an arithmetic operation or an algorithm, you need to hit these specific metrics. What is the time complexity, meaning how fast does this thing actually run? What is the space complexity? How much memory does it just devour? What are the edge cases we talked about, and what is the overall cascading effect on system performance? Examiners are actively looking for candidates who consider multiple solutions, who analyze the trade-offs between them, who openly acknowledge the limitations of their own code, and who justify their final decisions with hard, undeniable evidence. Deconstruct, solve systematically, check reasonableness, and make justified recommendations. This sequence is the absolute heartbeat of comparative analysis. And remember, when you are comparing 2 different algorithmic approaches or solutions, you must identify similarities and differences. It's not enough to just point out how they differ. You have to use comparative connectives in your writing, words like whereas, or in contrast, or similarly. And crucially, you must support every single claim you make with evidence extracted from the data provided in the question. Don't just assert that one algorithm is better or faster. Systematically prove it by checking its reasonableness against the data and making a fully justified recommendation. So, as we wrap up today's clinic, I want to leave you with a provocative question. Will your next exam answer merely state generic facts, or will it systematically prove your algorithmic methodology? Think about it. You now have the exact diagnostic tools the examiners use. You understand the massive 15% weight of these concepts. You know the procedural framework inside and out, and you know exactly what ailments and pitfalls to avoid. The cure to lost marks isn't just staring at a textbook longer or trying harder. It is evaluating, it's connecting, and it's applying your knowledge with absolute precision. Take this framework, apply it to your very next past paper, and watch your mark scheme absolutely transform. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.